Let's get started. Okay, so we're going to do some more optimization using concepts of control theory and describing a goal that we would like to achieve and then finding the commands that get us there. Oh. All right, so the material that we're going to cover is chapter 11. And I'm going to start us up with a specific example that it was a paper that appeared in Nature. I think it was 1998 or something like that. I'm not quite sure, and it was by Harris and Wolpert. And this paper is going to use the mathematics that are similar to what I'm going to show you today. We're going to do it a little bit better than they did, but that's just, just for you guys. So what was the problem that they wanted to solve? They said that, look, when you are attempting to move from here to here, if you look at the velocity profile that that movement has, the particular movement they were interested in were eye movements, and they were called saccades. And saccades are these fast movements that you make with your eyes when you're reading, for example. And they said, look, when you look at that velocity profile in time, maybe a saccade that takes usually, say, 60 milliseconds has a velocity that sort of looks like this. It has a peak velocity of about 500 degrees per second. This is how fast your eye is moving. And it has a particular shape to it. And they wanted to know, well, why is it that the nervous system moves the eye from this location to this location with this particular, velocity profile? Why doesn't it choose, something that looks like this, maybe, or, something that looks like this? It both gets you to the same location, but with a different path. And so what's good about that particular way by which you move? In this case, for an eye movement. So their idea was that the particular way that the nervous system moves your body is based on a principle that says there's noise in the nervous system. That noise causes variability from movement to movement. And what you're trying to do is to get to the goal, where the goal is, and to get there with least variance as possible. So we're going to set up the equation so we have noise, and that noise is going to cause variability. And then we're going to solve the equation and find the commands that you need to get you to the goal with the constraint that you're going to have as little as noise, little variability once you get there as possible. So the idea would be like you have a horseshoe that you're throwing to some location. So here's a stick here, and you're throwing a horseshoe. Here's a horseshoe. You're throwing it out here, and sometimes ends up here, sometimes ends up here, sometimes ends up here, sometimes here. And what you want to do is that you want to make it so that the variability is as small as possible, and it lands on average right on the target. So the expected value of where it ends up is right at the target, and that variance is as small as possible. That's the idea. So that's the control problem that we want to solve. Okay, and in this case what they did is for the purpose of a saccadic eye movement. And now what's important about the class of problems that we're considering is that they're open loop. What that means is that as the commands are generated, you have no feedback from the system about its state. So you can't alter your commands as you're generating them. That's an open loop controller. And the idea is that as you release this, horseshoe, well, the thing is just going to fly and get there. You can't do anything about that trajectory once it gets there. Of course, as your arm is moving, you get sensory feedback. Now, for saccades, because this is only 60 milliseconds in duration, from here to here, that is open loop in the sense that the brain can't get feedback from the muscles of the eye or from visual input on the eye because that's just too small of a time. And so, in a sense, it's open loop. You're just sending some commands out. And you want to know, well, what's the best commands that you can send out so that on average you land precisely on target and you minimize the variance of your movements. So, for us to solve the problem, we have to set up the dynamics of this system with noise, then describe what is the cost that we're trying to minimize, then describe the constraint that we have to have, and then solve the problem. Any questions about this? All right, so let's do it so you can see how to do it. Okay, so you have some dynamical system, and you have, mx double dot plus bx dot plus kx is equal to some force. So you have something that you're going to move, and that force is going to tell you how you're going to move it, and it depends on its position, velocity, and acceleration. And so therefore, acceleration is 1 over m force minus bx dot minus kx. All right. So how's force related to the commands you send? Well, you have some muscles, and you have maybe a simple model of a muscle where you have alpha 1 times f dot plus alpha 2 times f is equal to u. So that's the derivative of this. So this says that the command that you send, u, is going to generate some force. And what that means is that the change in force, f dot, is going to be equal to 1 over alpha 1 u minus alpha 2 times f. Okay, so this is the dynamics of our system. Of course, we wrote it in continuous time. So let's now let's write the state space model for such a system. So we're going to define some variables. This is called x1. Define this as position. x2. Define this as velocity. x3. Define this as force. So I have now x1 dot, x2 dot, x3 dot. So this is my state. Position, velocity, force. That's the state of my system. The change in that state I will write as a function of the state plus some function of the input u that you gave. So that's what I will need to fill out. So x1 dot is going to be velocity. So I'm going to have 0, 1, 0 here. x1 dot is equal to x2. x2 dot is acceleration. That's minus k over m times x1 minus b over m times x2, 1 over m times x3, 1 over m times force. Force dot is not a function of position, not a function of velocity, but a function of force, and that's minus alpha 2 over alpha 1. Okay, so now what about the input u? The input u only affects f dot, so that's a 0, 0, and 1 over alpha 1 here. Okay, so that's the dynamics of our system. You give it an input u, it causes a change in state. All right, but that's in continuous form. So what I have here is a vector x, which is my state, is change, is equal to a, continuous, times x plus b, which is a vector, continuous, times u. All right, so now I want to write this in discrete form. So I say, well, I have x dot is equal to x at time t plus delta minus x at time t divided by time delta. So that means that x at time t plus delta is x dot times delta plus x of t, which is equal to a continuous times x plus b continuous times u plus delta times that plus x of t, which means that x at time t plus delta is identity minus the time delta, the time step delta times AC times x of t plus time step delta times the vector b sub c times u. So that's equal to a times x plus b times u, where a is identity minus time delta times AC, and b is delta times BC. So all I've done so far is to write the dynamics of the system in discrete mode. Okay. Do you have any questions about that? What I did? So x dot is x at some time in the future minus current x divided by time delta. So from this, I can write x at time t in the future as a function of current state x and input u. So I went from discrete to continuous to discrete. Yeah.
So, and we assume that delta goes towards 0.
Yeah, the delta is small. So you know, however you're going to simulate your system, millisecond or something. Okay, so you know, this is how we get to the way we write things. X at time t plus delta is equal to a times x at time t plus b u at time t. So that's our system. Okay, so now we add noise. We have x at time t plus delta is equal to a x at time t plus b. And now what I'm going to do is I'm going to add two kinds of noise. U at time plus t plus epsilon u plus epsilon x. And I have epsilon u, that's a normal with mean 0, variance k squared u squared. Epsilon x is a normal with mean 0 and variance q. Okay, so that's our system. Now, what do we want to do with our system? Well, what we would like to do is to move to the endpoint G with minimum variance. So what does that mean? That means that you want that at the time, so when your movement ends, say the movement ends at time point P. So that's as long as you want the movement to be. At time point P, you want to be at the goal position. And what do we mean by goal position? Well, that's what we mean by that is that the expected value of x at time point P should be g. So x is a vector, right? X. What was our vector here? It is position, velocity, and force. So you want at the end of your movement to be at some state, and that's described by this goal. So typically you want to be at some position with 0 velocity, for example. That's what you want as being the end of your movement. That's the expected value that you would like to achieve. Under what does it, when you achieve this is your constraint. And when you achieve this, you want the variance of your endpoint to be as small as possible. So you want to have a cost that's going to be the variance of your endpoint. So variance is going to be just position, right? So you want just the position of your end to have smallest variance as possible. So I'm going to do that with a vector S transpose times x at time point P. And that, what I mean by that, S is a vector of 1, 0, 0. So what this does is that it just picks position and says only the variance of position is what I'm interested in. Of course, you can make it whatever you want. S doesn't have to be 1, 0, 0, but why not say that, you know, I want you to get to the endpoint with zero, with as small as a position variance as possible. That's what S does. So this is the cost that I want to minimize. Under this constraint. So on average, I want to land on target while minimizing endpoint variance. Let me stop to see if you have a question about that. Yeah.
Why is there S transpose again? 1, 0, 0?
So remember, x, the vector x was position, velocity, force. So what this is doing is it's just saying that what I want you to minimize is the variance of position. Does that make sense? Because that's what the goal is. Yeah.
Why we don't want to minimize the, for example, variance of force? Because when the
You can.
eye moves there, the force should keep the eye.
You can. You can. We're going to solve the problem for arbitrary s. But the way they solved it in that Nature paper was with position. Yeah.
So in this case, the position only has one component.
But it's 1D. Yeah. Our dynamics is one-dimensional. The state of it is associated with just position, and then of course it has velocity as well. You could, but you know, this would be easy to do it with 2D as well. Except that if you're going to define a cost, it has to be a scalar cost. So if you're going to have variance, then it has to be like, you know, some scalar measure of variance for a vector. All right. Good questions. Thank you, guys. All right, so how do we solve this problem? So now what I need to know is that, well, what is the variance at the end of my movement? What is the expected value at the end of my movement as a function of the commands u that you gave? Because what we have to do is minimize this cost with respect to the commands. So what do we want? We want u from time point 0 to time point p. That's what we're after. So to find those commands, we have to minimize our cost given that constraint with respect to the commands. So what I need to know is that, well, how does the endpoint variance depend on these commands? How does the expected value depend on these commands? That's what I need to write. So that's the next step. So how do I do that? Well, what you do is that you say, okay, well, x at time point 1 is a at time point 0 plus b u at time point 0 plus epsilon u plus epsilon x at time point 0. What's x at time point 2? Well, that's just a squared times this, which makes it a squared, x at time 0 plus a b u at time 0 plus epsilon u plus a epsilon x at time point 0 plus b u at time point 1 plus epsilon u at time point 1 plus epsilon x at time point 1. Okay, so in general, I can write that x at time point p is equal to the matrix A raised to the power of p times my initial position, my initial state, plus the sum of the following. Excuse me. This is basically a way to say if you have some history of the commands u, what's going to be the final position p that you're going to achieve. Okay. All right. So now we have two things that we want to know. We want to know what is the variance of S transpose x of p, and what is the expected value of x of p. If we have that, then what we could do is put it into our cost and our constraint, write a equation that has the Lagrange multiplier so we can incorporate our constraint into our cost, find the derivative with respect to u, and that would be the solution. Okay, so let's do it. Let's see what it looks like. So let's begin with the variance. Let's begin with this top equation. This one I'll do it for you later. Okay. All right, so the variance of this equation only depends on these noises. So we have the sum I have S transpose in front, A P minus 1 minus N, times, I have this term here, B, then I have the variance of this term, B transpose, plus I have the variance of this term, times A P minus 1 minus N quantity transpose times S. Okay, so that's equal to these terms here. This term becomes B times variance of epsilon u is K squared U of N squared B transpose. This variance is Q, and then these terms here. All right, so we've written the variance of endpoint in terms of the commands u. Then we have our constraint. Our constraint is that the expected value of x at time point p should be equal to the goal. Well, what's the expected value at time point p? That's just this term, a raised to the power of p times the initial state plus the sum all right, so that's where we would like to be while minimizing the variance. Okay, so now we have a cost, we have a constraint, so we put it together. So we say the augmented thing that we would like to minimize is variance of S transpose x of p plus our constraint, the Lagrange multiplier times the expected value of x at time point p minus our goal. Okay, so we would like to minimize this augmented cost, and so to do that we're going to have to meet two things. We're going to have dja du history. So this is with respect to all the commands u. I'm going to put DUH, where what is UH? Is a vector history of commands. U at time point 0 to U at time p minus 1. The derivative of this with respect to UH has to be 0, so this is going to be a vector where every single equation is equal to 0. Also, because we have a constraint, derivative of GJA with respect to lambda has to be equal to 0 as well, where lambda is a 3 by 1, because this expected value of x of p is a 3 by 1. So we have to meet both of these equalities. So let's do it. What's derivative of JA with respect to UH? So we begin by finding the derivative with respect to U0. The first term here. So that becomes 2 times k squared U0 times S transpose A P minus 1. So n here is 0 times B transpose A P minus 1 times S. Derivative of this sum with respect to U0 is just going to be this term. That's the first term in our Jacobian. This plus, we have lambda times this. This is going to have a u0 in it as well. So I'm going to have a second term. It's going to have a lambda transpose times A P minus 1 times B. That's our first equation. Derivative of this with respect to u1, 2k squared u1 S transpose A P minus 2 B transpose A P minus 2 times S. Derivative of this with respect to u1 is lambda transpose A P minus 2 times B, that's equal to 0. So you do this with all the u's and you get P equations. But you have how many unknowns? P plus 3 unknowns. So you also don't have lambdas. So you have to now find derivative of JA with respect to lambda. And that's just, of course, derivative of this function with respect to lambda is just this. So that's expected value of x of p minus g is equal to 0. That gives you 3 equations. So you have p plus 3 equations, you have p plus 3 unknowns, and you solve for your unknowns, u and lambda. So you find u0 u p minus 1, lambda 1, lambda 2, lambda 3, where this were our Lagrange multipliers. Okay, that's what you have for your homework, something like this. And then once you have the commands, you give it to the system and you look at its velocity, how did it move? Why did it have the shape that it does? And what you will see, the insight that came from this was that, look, when you have signal dependent noise, so when you have U that is corrupted with noise that grows with the magnitude of it, it naturally says you should produce as small of a force as possible. But then, you're trying to move from here to here. And there's some time that's going to pass as you make this movement. Should you produce big forces early, or should you produce big forces late in your movement? And it turns out that, well, if you produce the big forces early, accelerate early and coast, then the system is more likely to have a small variance because the commands that you're producing at the end are going to be small. On the other hand, if you move like this, then you're going to produce big commands at the end of your movement, which is going to result in large variance. So if you're going to move a system in order to have small variance, and that variance depends on the magnitude of your commands, it's better to generate that large magnitude things early on than later. Because early on, it gets damped out by the system. That variability gets damped out by the system. Whereas at the end, you have very little time left for the dynamics of your system to dampen the variability. So the insight that came from this paper was that maybe the brain moves the eyes the way it does because it cares about not just getting to target, but also get to target with minimum variance. Questions? So what did we do? We minimized the variance at the endpoint, given the constraint that on average we want to be accurate. We want to be unbiased. All right. Okay. All right, so this was an example of having a system where we didn't have a desired trajectory. We just had an endpoint. You know, that's equivalent to my problem of retiring Bahamas. Retiring Bahamas is an endpoint problem. I have no trajectory from here to Bahamas, right? I don't have a notion of what I should do so that from here on in my life, I will have some sequence of steps so that at the end I get to Bahamas. I've never been to Bahamas, but you know, I think it's a good example. So the idea that I just gave you was the notion that you have an endpoint constraint. So at some time in your life, you want to retire in Bahamas. Today you're here, and you want to know what are the commands you should produce so that at the end you get to Bahamas. Well, in principle, that's like a problem we just solved. But sometimes the problem is a little different. You also have a trajectory. So you have now a robot that has to weld something. And so it not only has to get to this point, but it has to also get to that point in a particular path. That's a trajectory. That's like when you have your parents tell you, in order to get to Bahamas, you have to pass the SATs with a great score. And then after that, you have to go to this school. And then after that school, you have to marry this person. That kind of stuff. So that trajectory is given by somebody, and you have to meet that trajectory. So how do we do that kind of a problem? Before we get there, do you have any questions? Yeah.
Do we have to put any constraints for use? For example, maybe we calculate a U that is not reasonable or practical.
Yeah. So in principle, U's play an important role here. You notice that my variance depends on U squared. And so in principle, this is penalizing big commands. So an additional constraint can be put in, but you already are penalizing things based on its size. Okay, so the second problem that I want to show is open loop with a reference trajectory. So maybe this is like your big brother or big sister that already has gotten to Bahamas through some path, and you say, okay, what do I have to follow that exact path. All right. So again, we have our dynamics. And in this case now, I'm going to make things so that these are vectors now. So this is an m by 1. This is m by m. And this is m by 1. And I'm going to have a output y. And y is a q by 1, let's say. So I'm not going to have any noises in here for this example. So I'm going to have y going from time point 1 to time point p, and I'm going to have input u going from time point 0 to time point p minus 1, and I'm going to have a reference trajectory r, which also is going to go from time point 1 to time point P. So the reference is specified in terms of y, which means that my cost looks something like this. Okay, so this is some trajectory cost, and there's some motor cost. So the class of problems that we're working for are called linear, quadratic regulators. And so linear in that the system is linear, quadratic because of this, right? You see that things are being squared, and regulator because we are coming up with a controller that could solve that class of problems. Okay, so our first step is write J in terms of U, and then minimize it in terms of U. So as before, we expand our state equation. So x at time point 1 is A times x at time point 0 plus B times U at time point 0. X at time point 2 is A times x at time point 0 plus B at U time point 1. So in principle, x at time point P is A at time point A raised to the power P times x at time point 0 plus times some sum J is equal to 0 to P minus 1, A P minus 1 minus J raised to the power of that times B times U of J. All right. So now what I'm going to do is to take this sum and write it in a matrix form. So I want to take this n position and write it in terms of the history of the input U that we've been giving to it, but not in terms of a sum, but in terms of a matrix. And so just this is going to involve a little bit of nomenclature. So let's define the vector. Actually, it's going to be matrix E as follows. Matrix A squared, A to the power P. Define matrix F as follows. An identity matrix, A times A and then an identity matrix, A squared, A, then an identity matrix, and so on. And then 0 like that. Matrix gamma as B 0 0 B 0 0 B 0, so forth. And so when I have that, F times gamma is B, A times B, B, A squared B, A times B, B, so on, 0 0. And so what we end up with, and this T here, sorry, let's go back to our, so this T is some matrix. which basically is like a weighting of the cost associated with the following the trajectories to some other matrix, which is the weighting of the commands. So I can now define another matrix, TH, which is just basically all the T's going from the first data point to the last. The reference history, R, going from time point 1 to time point P. And then finally a matrix G, which is basically C in the diagonals and 0 elsewhere. Okay, so all of this is done so that I can write the following. X, its history from time point 1 to time point end, can be written as the matrix E times the initial state x0 plus F times gamma times UH. And so basically XH is going to be x0, sorry, x1 to x of p. So I've written the history of x in terms of initial state x plus all of these commands u that you had, this equation here. The output y, its history, is going to be g times xh. And so now I'm going to write my cost function in terms of the input u and the output y. So the cost function j is y minus RH transpose times TH YH minus RH plus UH transpose LH UH. So I took the sum and I wrote it as a matrix system. And what I want to know is basically how do I minimize this with respect to the command UH. So let's write this now in terms of the quantities. So YH is G times XH minus RH transpose TH G times XH minus RH plus all right, so let's multiply it through XH transpose G transpose TH G XH minus 2 times RH transpose TH G XH plus RH transpose TH RH plus UH transpose LH UH. So XH is E, the matrix E times X0 plus F gamma UH. All right, so now what I want to know is that find the derivative of this, minimize this with respect to the command's history that you gave. So we'll find the derivative of this with respect to UH. Here's UH. And so that becomes the following. XH is going to have a UH in it, and that's going to get that's going to be a quadratic form in UH. So this doesn't matter. This is the one that we care about. So we're going to get a 2 in the front, and then you're going to have a vector form that has to end with UH. So it's going to look like this. let's find the derivative with respect to xh first, then we'll find the derivative of xh with respect to uh. So derivative with respect to xh is going to be gamma transpose f transpose g transpose t xh g xh minus 2 times RH transpose GF gamma plus the last term 2 times LH UH. Well, that's equal to this term times okay, so you solve for UH from this derivative, and we get basically these terms here, and then this term here. That's the terms that have UH in it. You get LH plus gamma transpose F transpose G transpose TH G minus 1 times this term here, gamma transpose F transpose G transpose TH RH minus G E x0. So it's this hairy equation, but basically it says you give me your initial position, you give me your reference trajectory, and I will give you the history of the commands. Okay, so that's another example of open loop control. You start with dynamics of a system that has input u and changes output y. You have a cost that says match a reference trajectory. Then what you do is that you basically write what's the history of my output in terms of my input. Here's that history. Then you write your cost in terms of the history of the input, u. Then you find the derivative of that cost with respect to the u. And then you know, in the case of the quadratic regulator systems, you can solve for u and you get the commands. And that's the reference trajectory that is transformed into the command history u. Okay? All right. So these are the class of problems called open loop control. And they're not very realistic ones because you never want to just send some commands and have nothing feedback to it. And so the interesting problems are the ones that have feedback. And then the problem becomes much more interesting because you say now, what's the policy that I should have? So you don't know precisely the commands you're going to have in the future. You're going to have a policy that says, if this is the feedback that I got about my state, this is the action that I want to do. And so to solve those kinds of problems, then we're going to need a different class of approaches, and that's going to be called the Bellman equation. And so in the next 2 lectures, we're going to talk about how to solve problems that says, here's my goal, and now what I want you to give me is that what is the best policy, not the best commands, because you don't know the feedback you're going to get. What's the best policy that's going to take me from beginning to the end so that it maximizes some utility? And so it's equivalent to the kinds of problems that say, you know, give me some principle with which to live with, and then I'm going to get to Bahamas if I knew that principle, so that I could figure out what's the best action to do regardless of the state that I end up at. Because you have a noisy system, you generate some command, it ends up at some state. Now that you measure that state, what is the best thing that I can do so that I continue along the path to get to my goal? And that kind of problem is a problem that is going to be in the field of dynamic programming using these concepts of Bellman equation. So on Tuesday, what we're going to do is we're going to imagine a game that we have to play. A game that says, here's how you win this game. Here's at the end you wanted to have something that says you have a game that you have won. And here's some costs associated with it. You find yourself at this state. What is the best thing to do? Now, you are far away from the end of the game. Can you come up with a policy that says no matter where you are, what is the best thing you should do so that at the end, if you sum up all the actions that you did, you not only end up at the goal state, but you get there in such a way that minimizes the cost associated with your actions. And so that's going to be the Bellman equation. And we'll see that we're going to have concepts like value associated with states and ways to then go from the end of the problem to the beginning and say, okay, I am here in Reza's class. He's taking some time to talk about some math, but I want to get to Bahamas. And so given that I'm here and that's where I want to go, what's the policy that will get me there? Policy meaning not the commands that you need, but how you should react to states. What's the best action you should produce regardless of where you find yourself? And so why is that useful? Because when you generate some action, the consequences of that are noisy. You can't, know for sure where you're going to end up. And so therefore, you need feedback. So you're going to sample what happened and say, okay, I am here now. What is the best action to do? And so we'll see that we're going to bring back the Kalman filter because you produce an action, you generate a consequence, you measure something, and then you have to combine what you measure with what you expected. And that becomes your estimate. And based on that and the Bellman equation, together you now have the best action possible. So all of this is going to come together in the next 2 lectures, and it's going to be a beautiful story. At least I think so. All right. Have a good weekend.